So in question 2, we have students conducting an experiment to determine the acceleration of a cart. The cart is released from rest from the top of the ramp, and we are defining the x-axis to be parallel with the ramp, and its origin is at the top of the ramp. The students collected these data, and in part 1, we need to indicate which quantities could be graphed to yield a straight line whose slope can be used to determine the acceleration of the cart. And we may record other quantities as well if they are not already in the table. So what we will need to plot here is position on the vertical axis, and horizontal axis will be time squared. In this way we are expecting a linear graph, and the reason for that is because position is equal to the initial speed times time plus 1/2 at squared. The initial speed is 0, therefore the position will be 1/2 at squared. So if we plot a graph of t squared on the x-axis, displacement on the y-axis, then this 1/2 a will be our slope, and so from that we can calculate a. So we need a column for time squared. Time squared, we'll have units of seconds squared. So we need to square all of these values in the table. So this will be 0.15, 0.35, 0.92, and 1.44. So this is for part 1. In part 2, we need to, on the following grid, plot the appropriate quantities to create a graph to determine the acceleration a of the cart. So we really just need to plot these values. So on the x-axis we have time squared. In seconds squared. On the vertical axis we have position, which is in meters. And then we can see, well, the position will go from approximately 0 to 0.6. So we can make each major break a 0.1 scale. Like this, everything will fit. 0.6, and for time squared, we go from approximately 0 to like 1.5, 1.6. So we can make each major point go up in 0.2. 1.4 and 1.6. So like this, all of the points will fit onto our graph. And now we know what we need to do is plot the points. So our first point is at 0.15. So 0.15 will be approximately here, and the position is 0.06. So that point will be here. And then our next point is 0.35 and 0.14. So that will be approximately here. And then our next point is 0.59 and 0.24. So that will be approximately over here. And our next point is 0.92 and 0.37. So that will be approximately over here. And then our last point is 1.44 and 0.55. So that will be somewhere over here. And then we need to draw a line that represents the data. So we can simply draw a straight line, which in this case seems to approximately pass through all the points, but it would also be okay if it doesn't pass through all of the points. We just need to draw a line of best fit. And then in part 3, we need to use this line drew in this part to calculate the experimental value for the acceleration a of the cart. So what we need to do here is calculate the slope of the graph. So the slope is simply the change in y over change in x. So what we need to do is pick 2 points basically on the slope, on the line itself, not using the points that we have plotted. We just have to pick 2 random points. So for example, we can pick a point at 0.4 and it's approximately at, let's pick this point. It has to be on the line, so that's important. This is 0.4, comma 0.18. You can pick another point, let's say at 1.2, comma approximately 0.48. So our change in y over change in x is 0.48 minus 0.18 divided by 1.2 minus 0.4 will give us an acceleration, a slope of 0.375 meters per second squared. However, this is not our acceleration yet because, as we've seen at the start of the question, s is equal to 1/2 at squared. Therefore, our slope is equal to 1/2 a. Therefore, for a, we still need to double this value, which will give us approximately 0.75 meters per second squared.